Welcome back. So, let us start with our transistor level analysis of the front end amplifier we are looking at. So, we can start the analysis with a simple common source amplifier with resistive load, and then go towards active load amplifier, which is ultimately going to link with our overall two-stage amplifier, with the help of which we are building our front end amplifier. So, here I have constructed a simple common source amplifier, and I can represent the overall noise constituent of these two resistors and the transistor over here. So, I can draw the noise source of the resistor, put it as 4 kT upon R. Likewise, I can put the noise current source of the transistor, put it as 4 kT gamma GM, and I have the 1 upon F noise, which is going to be given by K W L C O X times F. And since I have to get the effect of only the noise, I can set the input signal to be 0. So, I am not considering any applied input signal apart from this noise source that you have in the circuit, and therefore, I can find out the overall noise voltage at the output terminal. So, if I take the superposition, remember the small signal transconductance is not going to come into picture directly, because the VGS, there is no additional input signal coming because of the VGS, but only way that small signal transconductance is going to come is because of this noise signal at the gate. So, if I consider this as an input signal, remember that this is your VNG square. So, this is the mean square. So, in order to get the small signal current resulting from this noise voltage at the gate, I need to multiply this with the GM square. So, that will also ultimately add up as a small signal current in parallel. So, you have another small signal noise current, which is basically going to come from this input source, which is going to come from this input source, which is given as K W L C O X times F times GM square. So, there I can capture the effect of this noise in terms of a current. And as a result, if I look at the AC analysis, the overall voltage over here, I need to take up the summation on the square values. As we have discussed earlier, if you have uncorrelated noise sources, like the noise source at the gate is uncorrelated with the channel current noise, because the mechanisms are different, their origins are different, therefore, these two are uncorrelated noise sources. Likewise, the resistance noise is also uncorrelated with the other noise sources, therefore, these are three independent uncorrelated noise sources, and therefore, in order to get the final output voltage, I need to just take the sum of their mean square that I am automatically obtaining from this combination. So, I have the VON square given by the three noise sources 4 kT upon R plus let me call it K naught, so that it does not get confused with the Boltzmann constant, K naught W L C O X F G M square plus the 4 kT gamma GM times the overall the overall resistance at this point. So, these are the total current summed up, IN1 square, IN2 square, IN3 square, that multiplied by the total small signal resistance. So, this is nothing else but similar to our case where you have an overall resistance of the MOSFET, and in total you have some current coming over here. So, this is set to 0. So, I have captured all the noise sources, ultimately they are between the AC ground and the drain. So, all these three noise sources are between the AC ground and the drain. So, I have combined them into IN square, which is equal to IN1 square plus IN2 square plus IN3 square, IN1 square plus IN2 square plus IN3 square. So, this is I can call this IN1, I can call this IN2, and I can call this IN3, or other squares. And as a result, I can get the total IN square, and I have to find out the overall noise voltage coming at this point is just going to be IN square times the total small signal resistance over here. And once again, if the passive resistance is much smaller than RO, I can just multiply it with the R square that you have, the passive resistance over here. So, this multiplied by R square gives me the VON square over here, and this is the output noise. So, overall output noise. So, it can be termed as output referred noise. It means what is the overall noise voltage or the mean square value of the noise voltage, in other words, the RMS of the noise voltage produced at the output node, in case you do not have any signal applied. So, if you are just trying to read the noise voltage, sense the noise voltage, absence of any signal, this is the mean square value that we are expected to obtain. Now, another important quantity in analyzing circuits is the input referred noise. We want to find out the equivalent noise voltage at the input, which would produce the same noise voltage at the output, provided this was an ideal circuit, noiseless circuit. So, for that I need to translate this VON square, which is the output referred noise, to an input referred noise by dividing this entire VON square by the gain of the circuit. So, therefore, we are going to do, what is the small signal gain of this amplifier? This is just GMR. So, we are going to divide VON square by the gain of the circuit, which is GMR square, to obtain the input referred noise. So, R square term gets cancelled, and you are having the 1 upon GM square coming into picture, 4 kT R GM square plus K naught upon W L COX F plus 4 kT gamma upon GM. So, this is the overall expression that we obtain for the input referred noise. So, I can translate this into an ideal circuit, so that the transistors and the resistors are not noise free, but I am having an equivalent input referred noise VIN square, which is capturing the noise contribution of all the transistors and resistors in the circuit and representing it as an equivalent input referred noise, which would produce the same VON square, same output referred noise, provided this was an ideal circuit. And if you are having an input signal applied to this amplifier, which is very minute, we would like to make sure that the means RMS value of this input referred noise it is much smaller as compared to the input signal, so that it does not corrupt it. For example, if I want 7-bit precision or 7-bit accuracy in the recorded data, and the data coming over here is 1 millivolt peak to peak, I would like to make sure that the Vin, the RMS value of this noise that you are having at the input point, that is lower than 1% of that 1 millivolt. So, this should be within 10 microvolt peak to peak. So, the RMS value should be within 10 microvolt approximately to ensure 7-bit precision for the overall amplification. So, it is a good way to compare the input signal with the overall noise contribution of the amplifier. It can be done at the output node also. So, you can look at the amplified input signal and compare it with the output referred noise, or you can look at the input signal magnitude and compare it with the input referred noise of the circuit, and make sure that the input referred noise of this circuit is much smaller than the input signal that you are trying to process through this particular circuit. And now, if you look at the dependencies in this case, we can look at the GM and the R dependencies. We can see that all throughout we have 1 upon GM dependency over here, 1 upon GM square dependency over here. So, definitely having a larger GM for this device is going to help us in reducing the overall input referred noise. Likewise, if you look at the R term over here, it is coming as the denominator, and therefore, increasing the R term is going to suppress the input referred noise. And the reason is that this R term, although it is contributing to a RMS value given by root under 4 kTr, right. So, you have the mean square value given by 4 kTr, RMS value root under R, but the input signal is getting magnified by R. So, the magnification for the input signal is proportional to R. So, the input signal gets magnified by the factor R. So, if I am looking at the output voltage square with respect to the input voltage, that is having a dependency of R square, whereas the noise is having just a dependency of R, and therefore, the signal to noise ratio gets improved if I am looking at if I am using a larger value of R. So, despite this R contributing noise which has the mean square value proportional to R, since that is amplifying the input signal by R, it is improving the signal to noise ratio, and therefore, we can see that the R is coming in denominator. Larger R value is helping us in minimizing the input referred noise. And likewise, although the GM is contributing to this channel current source, since the GM is also conducive in amplifying the input signal, the output signal is directly proportional to the GM times the Vin. So, it is also amplifying the input signal, and as a result, we can see that having a larger GM is helping us in getting a better or a lower input referred noise, because it is the amplifier is able to amplify the input signal more strongly proportional to GM if the GM is larger. Likewise, we can look at an active load circuit where you are having a PMOS as an active load, and then look at the concept of the input referred noise of the common source amplifier with active load. Any question on this part before we proceed towards active load? Yes, any question on the passive load part? For the active load, once again I can put a PMOS and an NMOS and then look at their combined voltage sources, the noise voltage sources. So, once again I am going to have the Vn, we can call it Vng P square, and then you are having the channel current of the P MOSFET. Likewise, you have the channel current of the N MOSFET and the Vng N square. I am just denoting these terms, and the channel current over here we know that this is 4 kT gamma GM2. If I call this M2 and call this M1, likewise here you have 4 kT gamma GM1, and by doing a similar analysis we need to find out the output noise voltage over here or mean square voltage over here. Now, if you look at the Vngp square, we know that this value is Kp upon WL of P. So, I can call it WL 2 W2L2 COX times F. Likewise, this is Kn upon W1 L1 times COX times F, and then I can translate these two gate voltages also into the channel currents, just like we did in the case of the passive load by multiplying with the GM square. So, as long as the transistor source is grounded, we can directly convert the gate voltage into a channel current, because ultimately that noise voltage at the gate appears as VGS. So, it is easy to convert it directly into the GM times VGS. So, or GM square times this Vngp square gives me the equivalent channel current. Likewise, for the NMOS also the source is grounded. So, as long as the source is grounded and you are having the gate signal, in this case the noise which is having mean square value Vn square Gn, that you can convert it into an equivalent channel current by multiplying with Gm, because any gate signal multiplied by Gm square will give you the equivalent channel current. So, as long as the source of the NMOS and PMOS are grounded, you can do that, but we will see that if you have some other circuits where you have some transistors where the source is not grounded, like a cascode device that we have studied, there we cannot apply the same thing. There we need to look into some other considerations while translating the gate voltage into channel current. For these two, it is clear to see that the gate voltage can be translated into the channel current, and therefore, I can write down the equivalent noise current coming because of the gate voltages translated into channel current. This becomes Kp W2 W2 L2 COX F times the Gm2 square, and likewise this becomes Kn Gm1 square W1 L1 COX F, and ultimately we have the same scenario as the previous case, and what we are going to do is we are going to get the total output voltage VON square, which is going to be the combination of all these 4 noise currents. So, I can call these currents as IN1 square and IN2 square, likewise IN3 square. These are mean square values of the noise current, IN4 square. So, ultimately these are the 4 noise currents which are flowing from the AC ground towards the output node. So, if I look at the equivalent circuit, it is nothing else but the 2 MOSFETs, and an equivalent noise current source given by IN1 square plus IN2 square plus IN3 square plus IN4 square flowing from AC ground towards the drain, and all we need to do is find out the output noise voltage VON square, just like we did in the previous case. Only thing is, in this case we have an overall small signal resistance over here given by ROP parallel RON. So, all this current IN, I can call this ION square, that will be multiplied by ION square times the output impedance, which is RO1 parallel RO2 square to give me VON square, right. If you have an overall small signal current over here given by ION square multiplied by the small signal resistance of these transistor RO1 and RO2. So, that is also between the drain and the overall AC ground. So, I can further simplify this and I can just represent this as ION square and RO, which is basically RO1 parallel RO2, and we are finding out the output noise voltage over here. That is the equivalent circuit we have, and I can find out the VON square equal to ION square multiplied by RO square. And then in the next stages that we need to look at the input referred noise. So, for that once again I will divide this entire VON square by the gain of this circuit, basically gain square of the circuit, which is GM square RO square. So, if I have to get back to IVIN square, there once again I will look at this quantity divided by GM square times RO1 parallel RO2 square. So, basically in order to get the input referred noise I have to get the ION square divided by GM1 square, that is the quantity we are interested in order to obtain the input referred noise. So, let us find out the expression for this total input referred noise, which is ION square divided by GM1 square. So, all you need to do is just sum up all these 4 components of the noise and divide it by GM1 square. So, if you look at the 4 kT term, this is going to give me 4 kT gamma GM2 upon GM1 plus 4 kT GM1 square 4 kT gamma upon GM1, and then the other 2 terms, which is basically Kn upon W1 L1 COX and F plus Kp GM2 square upon W2 L2 COX F times GM1 square. This is the overall expression that I get for the input referred noise, and from here I can look at the find out the expression for GM1 in terms of WL and the parameters of the MOSFET, the bias current of the MOSFET, and arrive at the dependencies, how this overall input referred noise depends upon the sizing factors and the bias current of the circuit. So, here we are seeing that the GM1 square, if you increase the GM1 square, definitely the first term diminishes as well as the second term diminishes. So, we can rely on larger GM1 to suppress the first 2 terms, that is obvious, and lower GM2 over here to suppress the first 2 terms. GM2 is also coming over here in the second term. Therefore, we need to look at the second the last term also in order to decide about the GM2, but for GM1 we are confident that having a larger GM1 suppresses the first as well as second term. And the dependency point of view, if you look at the dependency here, you have GM1 square dependency. Therefore, if you increase the GM1 as compared to GM2, definitely this term goes down, gets suppressed. Likewise, the second term goes down linearly. So, the first 2 terms are relatively straightforward to look at, and remember the currents in both of the transistors are same. So, the way we have biased them, they are common source amplifier, load transistor and input transistor, and therefore, the currents are same. So, the only factor that remains is the W by L ratio and the constant terms like the mu P C O X, which are just constant factors. So, I can write it down 4 kT gamma, and here you are going to get let me write it down as root under the constant terms. I am writing it as Kp, and then you have I d, which is going to be here times the W by L of this MOSFET 2, and likewise in the denominator side I have the Kn times I d times W by L of MOSFET 1. Likewise, the second term also same thing, 4 kT gamma Gm and root under Kn I d W by L 1. And the last second term, once again it is already simplified in terms of the W by L, W1 L1 COX times F, and the last term we need to break down the GM2, which is going to have W by L 2 component. So, W2 over here gets cancelled, W2 of GM2 and W2 over here will get cancelled. So, you are left with only L2 over here and another L2 coming from GM2. So, it becomes L2 square. So, you have Kp upon L2 square coming over here, COX and F, and then you have the GM1 term coming again as Kn ID W by L1. So, these are the 4 terms that we are getting ultimately, and from the point of view of sizing, we can see that for the load transistor or the PMOS device, having a larger L2 is going to help us in suppressing the 1 upon F noise component. Likewise, having a larger W and L, having a larger W and L for the input device is going to help us in suppressing the 1 upon F noise component. Likewise, the thermal noise or the white noise component can be suppressed significantly by increasing the ID as well as the W by L. So, here also you have root under ID dependency, and everywhere ID is coming the denominator. So, by increasing the ID you can significantly suppress the thermal noise floor of the circuit. So, we can rely on relatively sufficient ID and a larger W by L to suppress the white noise floor, and at the same time we can rely on a longer channel length for the load device along with the ID and W by L of the first stage, which is anyway suppressing the 1 upon F noise, to reduce the overall 1 upon F noise component. So, if I look at the 1 upon F noise term, increasing W by L or W as well as L of M1 is having similar effect on the on all the terms. However, if you are looking at the last term over here, L1 is coming in the numerator. So, therefore, once again it can degrade the noise if you are just increasing the L. So, for the input device it will be more efficient to increase only the W, so that the 1 upon L1 term over here and 1 upon L1 term here, that does not mess up with the noise. So, I can go for a large W1, I can go for a larger sufficiently large ID, I can go for a sufficiently large L2 in order to reduce all these 4 terms. So, a larger W1 and larger ID is going to suppress the first, second as well as third term. Larger L2 is going to help us in strongly suppressing the last term over here. So, we can see the design direction that we can obtain from this computation in order to minimize the input referred noise. And another very important concern happens to be the 1 upon F noise corner that we have discussed. So, as we see, the 1 upon F noise term over here will go on increasing as we go towards lower frequency, whereas the thermal noise floor, that is constant. As a result, if we want to look at the corner frequency, where is the intersection of this 1 upon F curve, intersection of this 1 upon F curve and the white noise curve. So, as we go towards higher frequency, the 1 upon F goes down, as a result its magnitude diminishes, whereas at and therefore, the white noise becomes dominant, and this is the frequency Fc or the corner frequency below which the 1 upon F noise term becomes very significant. And if you are processing certain signal, if we rely only on sizing, then we would like to make sure that this Fc or the corner frequency is lower than the signal content, and also we would like to make sure that this white noise floor is having much lower magnitude or much lower RMS value as compared to the input signal. So, but the white noise value, as I see, is depends upon the first 2 term. So, having a larger ID and larger W by L ratio of the first transistor is definitely going to help us in reducing the white noise floor. Likewise, if I look at the 1 upon F terms, having a larger W by L ratio of the first transistor and also having a larger L2 term is also going to help us in minimizing the contribution of the 1 upon F noise term and push this frequency towards lower values. So, these are the two considerations we need to make while arriving at the design, minimizing the white noise floor and trying to suppress this corner frequencies to a lower value. And in general, we will see that for signal which are having very low frequency content, it may not be feasible or practical to push it towards much lower frequencies. In designs, it is convenient to push Fc to 100 hertz or even down to 10 hertz, but below that it becomes very challenging. So, up to few tens of hertz you can get it. down, but below 10 hertz it becomes very challenging, or it will start burning a lot of it will require a lot of bias current, or it will require impractically large sizes of this LNW to push the FC below say 10 hertz. Therefore, if your signal content is below 10 hertz, then we need to take care of some other schemes to mitigate the effect of this 1 upon f noise, and look at the 1 upon f noise contribution, the chopping frequency, the other schemes which can be applied to mitigate this. So we have looked at the sizing considerations. That's from the point of view of sizing, you can minimize the thermal noise contribution and try to push the 1 upon f noise towards lower frequency. But if your signal content lies at even lower frequencies, then what are the steps to be taken? So we need to address that. And also then we need to look at the differential amplifier configuration, then look at how the noise contribution of the transistors affect my response of the fully differential amplifier with which we are building our op-amp. So at the starting point, we can say that ultimately the differential amplifier for the differential response is having an AC ground over here, so it boils down to the same common source amplifier. So it should not create a lot of difference, but only a minor point need to be addressed, like the tail current source. So that that is another small issue that we can address.
Proceed. By F noise is due to trapping and releasing of the electron, but for PMOS, is there any there is no gate voltage is not changing or active?
No, but continuously there is always a so it's not only signal dependent. Randomly also you have under equilibrium you have trapping going on. Gate signal, when you apply the gate signal, it is changing that trapping process. But when you have two opposing phenomena going on, trapping and retrapping, it reaches an equilibrium where the trapping and retrapping is equal in magnitude. That only means that the mean value of the noise that is produced, that is 0. That doesn't mean that the amplitude is 0. So we said that the noise signal is having mean value 0. That means even if there is no signal, the trapping and retrapping is going on. That is not dependent upon the signal. Only thing is, when your signal is having such a low frequency content, it is overlapping with the frequency content of this trapping retrapping process. It can get corrupted much more. Okay, so we can take a short break, and after that we can get started with some of the remaining analysis in terms of differential amplifier operation and our operational amplifier circuit.